When we picture the solar system, we usually imagine a set of static rings. But out there, it's a constant, high-speed dance of orbital clockwork, with planets continuously shifting their physical positions relative to one another. If you ask almost anyone which of those planets is our closest neighbor, the answer you'll hear is Venus. This diagram makes the assumption intuitive. Venus's path comes within 0.28 astronomical units of Earth's, but planets rarely sit at minimum distance. For most of its orbit, Venus is on the other side of the Sun, putting millions of miles between us. Measuring the gap between two static tracks on a map does not tell you the practical, everyday distance between two moving objects. To find out which body is truly closest to us, we must stop looking at fixed orbits and track continuous physical motion over time. Those swirling clouds of Venus might have an orbit that flirts with ours, but the planet itself is usually millions of miles out of reach. This is why space agencies and astrophysicists have started prioritizing time-weighted spatial proximity, a metric that calculates the average distance between bodies across their entire orbital lifespans. Identifying our true neighbor requires a mathematical model that averages distance across time, rather than relying on a single snapshot of closest approach. The geometric solution used to calculate this time average distance is called the point circle method. This geometric model demonstrates the method. It works by treating one planet as a fixed point, and then drawing a line to every single infinitesimal position along the second planet's circular path, calculating the average of all those lengths. Traditional Keplerian orbital mechanics often use techniques like the patched conic approximation, which isolate only specific regions or points of gravitational interaction. The point circle method looks at the whole picture. This plot represents the result of that averaging. Because the calculation accounts for every position around the circle, the final distance is a direct function of the inner planet's radius. Specifically, as the inner radius r gets smaller, the average distance to any outer point drops. Because this value increases alongside the orbital radius, a smaller inner orbit mathematically results in a lower average distance over time. Geometry dictates that the planet with the tightest, fastest path will spend the most aggregate time near any other outer point in the system. That brings us to Mercury. It has the smallest orbital radius and the fastest orbital velocity in the solar system. Whipping around the Sun in just 88 days, Mercury continuously resets its proximity to other bodies, constantly sweeping back onto the near side of the solar system. This chart compares the true time average distances between planets. When applied to Earth, the math confirms that our average distance to Mercury is significantly shorter than our average distance to Venus. This holds true for Mars as well. Mercury's hyperactive orbit ensures it spends more time close to the red planet than Earth or Jupiter do. In fact, we can expand this outward. Mercury's rapid geometric frequency makes it the closest average neighbor to Jupiter, Saturn, Uranus, and even Neptune. Mercury's geometry makes it the primary point of proximity for every single planet in the system. Theoretical math is one thing, but recent AI-verified simulations using supercomputer data have run the complex n-body gravitational problems to back this up. This comparative chart illustrates a metric called proximity percentage, which measures how often one planet is the absolute closest to another. Mercury is Earth's closest neighbor over 45% of the time, heavily outcompeting Venus. These calculations even account for advanced relativistic shifts, like the gradual precession of Mercury's perihelion, the way its elliptical orbit slowly rotates around the Sun over decades. These simulations provide a more accurate look at planetary proximity than the distance charts found in older references. This geometry matters practically when we try to communicate across the solar system using the deep space network. Radio signals travel at the speed of light, which means signal latency is entirely dictated by physical distance. Planning reliable data relays requires knowing the true average proximity of your target. As we look toward missions like Artemis 4 and the expansion of human presence in space, Mercury's highly predictable proximity makes it a mathematically ideal anchor for future communication hubs. In a dynamic universe, proximity is defined by the companion whose path crosses yours most often.